Okay. All right. Well, welcome everybody to our last SIGTYP lecture of the year. And I want to welcome Liz or Elizabeth Salesky, who is someone we did our master's together at Carnegie Mellon, and a good friend and a Duolingo superstar. But her official bio says that she is a third-year PhD student at Johns Hopkins, and she's interested in machine translation, language representations, and how to make more data efficient models which are robust to the variation that we see across different languages and data sources. So without much more, let's welcome her, and she'll be sharing her screen shortly.
Alrighty, so here we are sharing screen. Hopefully everyone can see. Excellent. Okay, so yeah. To jump right in, I will be talking about how we can look beyond Unicode for open vocabulary text representations. And most of the work from this is drawn from a paper with Dave Etter and Matt Post this year at UNLP. And all right, I will pause and hold questions throughout when I pop up holding the question branch. So I'll make sure that if anybody has any questions throughout, we can address them before moving on. Cool. Okay, so to jump right on in. Part of the motivation for this work is pretty common. We want our models for text to be able to represent any word in a given language. So this is the concept of open vocabulary modeling. We want to be able to represent and handle unseen words at test time, in addition to things that might be rare or composed of things we've already seen. A number of common solutions to do this involve a character-based or subword-based vocabulary so that unobserved tokens can be broken into things that have been observed and therefore hopefully be handled by our models. Of course, this can come with a couple of potential issues, one of which is robustness. Just because we have the component units in our model vocabulary doesn't mean our model knows how to handle them in a new context. And as well, we have a predetermined vocabulary. So usually we might enumerate all characters in a given language or all the subwords that we get from a particular data set.
Yeah. Have you been switching slides, or is it still on the first slide?
Oh, interesting. I have. I'm on the motivation slide. Do you guys see the motivation slide?
No, we just see the title page.
Okay, well, that's an interesting one. Let me try resharing. We'll see what happens. Cool. All right.
I've seen this problem before. Are you on a Mac?
I am on a Mac.
Yeah. Sorry, I've seen this problem, but that doesn't mean I have a solution. I remember someone struggled with this at a talk I attended in the past.
Okay, I haven't had this happen before, which is interesting, but I think
is
I'll
this
just try...
Keynote?
Yeah, it is. Interesting.
Maybe the best is to export it to PDF. I don't know if that's easy or not. I don't know. Just from experience, yeah. This seemed to be tricky and happened several times to a person that gave a talk. I don't remember when, using Keynote on Zoom.
I wonder if it's a versioning thing. Yeah, I haven't had it happen before. I will try one more thing, which is just sharing the desktop instead, and then I'll back off to sharing a PDF.
Yeah, that should work, I think, the desktop thing.
Yeah, okay, cool. So let's do that. Sharing screen, sharing my current desktop. You guys see the first slide. Okay, now I have moved to the next slide. Does anyone see a change?
I see the pop-up of the EMNLP. Oh,
okay.
Yeah, we see changes. Yeah,
it's a little
awesome. Okay, if at any point it seems like things should have been changing and they were not, please just unmute again and let me know. Cool. Okay, so I will maybe give this slide again now that you can see it. So, right, our motivation is a pretty common one. We want our models to be able to represent all words in a given language. So this is, the concept of open vocabulary modeling. We want to be able to represent unseen words at test time. And two common solutions for this are character-based and subword-based models. so that unobserved tokens can be broken into things our models have in fact observed before. But two potential issues are robustness. So just because our model can use representations it has, doesn't mean it's going to be able to use them well. We may not be able to handle different combinations of characters in novel contexts. And as well, we're predetermining our model vocabulary. So for example, we might enumerate all possible characters that we see in training data or for a given Unicode range for a given language and use those as our model vocabulary. But if we have a completely unexpected character, for example, something from another language's range or even just noise from the web, we might still have unknown tokens. So to recap, we have a number of potential issues here. So subword-based models exhibit divergent representations as soon as the character sequences we see in new data are mismatched from what we see in training. So for example, this could be vowelization, where we have insertions through the sequence. And so this will cause a very different BPE sequence than if we saw the same word unvowelized in training. Minor misspellings, visually similar characters, and shared character components are all things that we as humans handle very easily, but cause very different representations for two otherwise similar words. To dive into this a little bit more deeply, so for these two example words, we've enumerated all possible consecutive subwords, and you can see that even though they're the same word, they have very few subwords in common. For visually similar characters, we might think of this as something like leet speak, which is, rare and unique to, for example, informal settings or internet text. But for a number of languages, this is potentially something in common use. So here, these are visually identical to me, but they have different Unicode code points. When we add diacritics, where we can compose one character from multiple different Unicode code points, we again have many possible sequences, and on with many possible different ways to represent the same thing visually, but underlyingly, our models are going to see different sequences. And this can happen if there is, for example, not one adopted standardized keyboard for a given language. If people have a tendency to use multiple keyboards, maybe switching back and forth between things that are well supported, and can cause a lot of problems for downstream text models. So, two motivations. These subword models that rely on exact character matches have robustness issues. And we've seen that visually similar text may have similar meanings. So we're going to combine these two things and come up with a new approach, which is hopefully going to be more robust. And as a side benefit is tokenization free and open vocabulary. So what is that? Here I'm talking about visual text representations. So what that really means is that we're going to take text and render it into a visual image at the sentence level. So given a particular font of a particular size, the entire sentence is going to be rendered to an image, which we will then extract slices from according to a fixed window size and stride. So you can see that these are, in fact, overlapping sliding windows. So this is drawn from speech recognition, where this is a very common way to extract features. And then similarly, we can extract features from each of these image tokens using things like convolutional layers. So, alrighty. Why do we render the entire sentence as opposed to, say, rendering the character or word level? There are a couple of reasons, one of which is that many scripts have contextual forms and require context to render correctly. So for example, in Arabic, characters can appear differently based on whether they're in isolation or in context and what that context is. As well, rendering diacritics individually is going to place them incorrectly compared to where they should be with the base character. So to render correctly, we need the full sentence. So you can see if I render per character, we have a poorly formed sequence. And if I actually take into account context when rendering this text, we have the correct expected sequence here. As well, many languages don't mark white space. So if we render the entire sentence, we're not upfront making commitments to certain segmentations, which might not be ideal for that particular language. All right, so combining this with a model, we are first rendering text to an image, extracting slices, and then these are being passed to basically feature extractor layers with some amount of convolutions. And then these are passed directly to a standard transformer model for, in this case, translation. So we're extracting our representations and learning them jointly with the downstream task, which ultimately is not so different from learning embeddings. But here, of course, we're using a slightly different input and not committing to a certain number of characters or subwords up front. All right, any questions about the model architecture itself or motivation? Awesome. In that case, I will continue on.
Can I?
Oh, yeah, go for it.
Sorry, there are a couple hands going up here. I
okay.
can moderate. So first we have Alok.
Yeah, I was just wondering, like, did you have to make a choice of a font, and how did that vary across languages?
Yeah, that's a really good question. So for all of these experiments, we use Noto Sans because it supports all of the languages we experimented with. We wanted to try to make sure that we were not introducing differences based on font, but obviously different fonts will render things very differently. So this will come up a little bit later with noise. So for example, if I have something like Leet Speak, it's going to be the case that certain characters look much more like the ones that they're being substituted for in certain fonts. So yeah, that's a really good point. But yeah, we used one font just because it had the largest coverage we were aware of. But things you could do would be mix fonts or experiment to see if there are font specific patterns learned maybe. Yeah.
Great, and then Levon has a hand up too.
Right.
Yeah, I was wondering, because you've talked about Arabic as one of the languages you've experimented with, which Arabic is written right to left. So does that change how the input works?
So it doesn't. That's a great question though. So we essentially, there's a character that says that this should be rendered right to left in the Unicode sequence. And so the input ends up rendered flipped right to left. And we extract sliding windows in basically the same way. But yeah, it was something to double check for in the rendering process for sure. Yeah.
Oh, interesting. Thank you.
Yeah.
Okay. Yeah, I had that same question too. So thanks for answering that. Anybody else? Also, we do see the
video box
things. Yeah.
Okay, I just propped it up so I could see the hands, but I will put it back down and hopefully I guess if you can moderate, that'd be awesome.
Yeah.
Cool.
Okay, great. We can continue. So thanks.
Sounds great. Alrighty, so let's talk about how to actually evaluate and compare visual text representations. So for our experimental setup, all of our experiments were done for machine translation. And so one of the things that we wanted to make sure we considered was multiple languages, not just for multiple scripts, but also for different morphological or syntactic features. So for example, if this only works in concatenative languages or something like this, we want to know. And so here we have 7 source languages, and for all of these experiments, we have the same fixed target language. So we're really just evaluating these as source representations. We're going to look at 2 different data sets. So we have a smaller and a larger setting. And the smaller setting with TED Talks covers all 7 of our source languages. The larger setting, only Chinese and German. And then finally, the architecture. So basically, we're using the architecture I mentioned a few slides ago, where we're adding a few convolutional blocks, so as feature extractors on top of a transformer. How many to use and what parameters might be significant for this task with this different way of extracting representations was something we really didn't know up front. So we experimented with a bunch of different combinations, and we'll go through that a bit in a few slides. So to start, we used text model baselines. And so here what you can see is that we're comparing all possible kind of character or subword based settings on the source side. So we've got characters, many different BPEs, segmentation sizes, and words. So that we know, for example, if the segmentation that we choose for our visual text is actually compared against the best setting from this, and if there are any correspondences from the way that we choose our window size with, for example, BPE length. So what we found is that we could use separate vocabularies for our source and target languages without affecting performance, which is awesome because then we can have a direct comparison with visual text. So we're using exactly the same target vocabulary on the English target side. And the only thing that's being varied here is how we represent the source language. And so, yes, what we see is that a pretty small BPE vocabulary is optimal for basically all of our languages. And so we pick the best one of each of these for all of the experiments going forward as comparison. So to start on our smaller data setting, what we see here is the text subword model that is best for each language pair compared with our best visual text representation model. And what we see is we're approaching parity, but there are still slight gaps, though also slight improvements for one or two language pairs. What we find is that the best visual text models use only one convolutional layer. So this is nice in the sense that we have lighter weight ways of extracting representations. And also interesting because it suggests that we really don't want to be allowing our model to kind of overfit on the visual representation side. We don't have a ton of layers dedicated to this extracting representations. And when we do, we actually see slight degradations in performance because it overfits to things that don't matter for the downstream task. So this is a great place to start. We're doing pretty well. And let's turn to a larger data setting to see what happens. So that is in fact the next slide right now. I'm just going to prove the point, I guess, of adding more layers for the visual features doesn't actually help. So this red set of lines actually has slight degradation in almost all cases, as does having no convolutional layers. And so that's essentially just passing a vector of pixel values through a linear layer to get an embedding size, and that's it. And so it seems like we might not have enough data in this setting to allow that to perform quite as well as something that has a little bit of a structural bias, which is a convolutional layer. Cool, all right. So on a slightly larger data setting, here we have about 10 million sentence pairs. We see similar trends. We're on par with text models, a little bit behind for German, a little bit ahead for Chinese, which suggests that it might scale. So hopefully the usefulness of this approach isn't limited to just lower resource settings, though of course that would also be very useful for many languages. One thing that's interesting is that we do see with more data, the having no additional convolutional layer is typically a little bit better. So it might be the case that, in fact, a slightly more data-driven model can do better. It just requires more data than our TED Talks allowed. So cool. All right. This is our base case. Let's talk a little bit about what's going on. So where are improvements coming from in these settings? We've made two main changes. We are using visual text representations And as well, we're also using a slightly different way of tokenizing. And by that, I mean just taking our sequence and breaking it up into tokens. So here we try an ablation where we remove the visual representations and only use basically sliding window segmentation on text. So we figured out what the best window setting corresponded to in terms of the number of characters that were covered, and it seemed to be about character trigrams. So we run experiments with character trigrams. And what we see is that for a number of languages, this is actually about equivalent to our visual representations full model. And in some cases, really just German, I guess. It's actually a little bit better than our best BPE model. However, there are many situations in which this is not the case. And so for 3 language pairs, we have a dramatic drop off in performance. Why is this? It seems to be the case that for the languages with more uniform token frequencies, character n-grams can perform nearly as well as BPE because all of the tokens we observe happen enough times our models can figure out what to do with them. For those languages where this is not the case, and there are many embeddings which are not seen enough times, we aren't able to do very well. So, all right, what happens when we introduce noise, for example, or a robustness challenge? We see that character n-grams actually have worse performance than both the visual representations and BPE models. And we'll get more into that comparison in a little bit. But this is particularly interesting because it suggests that of the 2 major changes, it really is the visual representations that are causing our models to do as well as they are. All right, so just to quickly summarize that, this set of experiments suggests that of the visual text representations, it really is the visual features that are the main source of improvement, not, for example, the sliding windows. And again, why is that? Languages with slightly more uniform character n-gram frequencies did a lot better in this setting. Worse languages and we saw worse results from languages with many poorly trained embeddings. So the crucial thing here is that character n-grams like BPE have no access to token composition. So whatever characters are within that subword, that information is not really included for the model's purposes. Whereas for our visual text representations, they are, because each set of pixels is actually corresponding to what characters are included in a particular image token. And so the models have direct access to some of that compositional information. All right, are there any questions about these initial results or the ablation just now?
Maybe I can start us off.
Sure.
I was noting that the Japanese, Korean, Chinese that have a different result, like their characters that are built also vertically as well as horizontally, and again, like Chinese has radicals and you would put them together differently than sequential. So is that you probably thought about that, right?
Yeah, so a couple things that can go on here. So this is one of the reasons we wanted to try, so many different language pairs. And some work has been done in the past on trying to extract visual features of characters for translation. So people have tried to map Chinese characters to radicals and then translate from that sequence of radicals, things like this. But yeah, so the way that that comes into play here, so we tried a bunch of different convolutional kernels to basically see if it's important for some languages that we, for example, grab horizontally or square subsections of the image tokens, which might be dictated by the way that the characters are composed. And I guess kind of interestingly, and I don't have a personal explanation for this, we saw the same kernels actually were clearly best for all of our language pairs. And so that's actually just a a little 1x3 rectangle. So it doesn't necessarily seem to be the case that adding information about like how a character is vertically or horizontally composed within the image token helped. Is it the case that that might still be affecting our results? Yeah, totally. For example, even if we use exactly the same font and font size for different languages will have different kind of ratios of how much of the pixels in a given token are actually being used versus not for character information, and some might be more compressed. So we also have a bunch of experiments like checking to see if we need actually larger font sizes or different like window sizes or ratios for different languages. And so, yeah, so what I'm showing is the best results for each language pair, but yeah, I guess I'd have to do a bit more digging to see if there are any systematic ways that the way that characters are written or composed are really affecting these results. It is the case that, for example, we have a slightly higher gap for some of these languages like Japanese, though interestingly, the language we do best at here on our TED Talks, for German, we're actually a little bit ahead, and Chinese, we're a little bit behind. As soon as we add more data, Chinese starts to improve and actually does better than the BPE models where German was a little bit behind. So some of it seems to be a little bit data set driven and like just based on the frequency of what we see in training. Yeah, that was kind of a long answer, but I hope that helped.
Oh yeah, thanks. I mean, I appreciate, yeah, a lot of decisions to make in this kind of new direction. So, okay, and then Alok raised his hand.
Yeah, I probably just missed this, but
Yeah, go for it.
could you briefly say what kind of noise it was again?
Yeah, so that was a quick pop-up preview, which I think actually in the next section I will go into in depth. So hopefully it'll be answered in a couple slides. But this is essentially just a small character permutation noise. So for example, we're taking two characters per token with probability of 0.5, and we're permuting them. And so, yeah, that that will impact a little bit the distribution of performance degradations we see across the different languages. But actually, the next section will be all about robustness. So we'll be able to see a little bit more if things are language specific or noise type specific. But yeah, that was a detail I did not, I glossed over initially. Yeah.
Great. Any last questions here? Okay, I think we're good to move on.
Perfect. All right. I'm just going to very quickly run through some technical details. I imagine more so than actually absorbing what these are, it'll just let you know if you have questions for the future where to refer to in case you're curious. So a couple technical choices we had to make as we went along were which hyperparameters actually mattered and how many require tuning. Things like training and inference speed. So for example, one of the common complaints about character-based models is that they are much slower to train than subword-based models. And here we're introducing rendering. So how does that actually play in? And then finally, does this really change the size of our models? So I'll go through these quickly, but feel free to ask me questions if you have them. So it turns out that most of the things we tested actually were pretty stable. So we saw different hyperparameter ranges gave the same performance. So what actually were these? These were things like in rendering text, the font and the font size, in doing image token segmentation, the window size and stride. So how far we move our window along for each token. And then for the actual visual architecture, we have the number of convolutional layers and then the convolutional kernel size and stride. And so most of these we found weren't really significant as long as they were not set to, very small or very large sizes. So for example, as long as you had a font size of at least 10 PT, you're good to go. And so for these two remaining ones, we did some tuning and found that there's pretty consistent ranges that are necessary. So for example, as said before, we really just need one convolutional layer to do about as well as we can. When you have more data, you don't necessarily even need this one. And we ended up with a single best kernel setting, which was a small square. The window size is most language specific, and one might wonder if this is perhaps related to the language's morphology. But we saw that the differences between languages and the best settings were pretty small. So there's a pretty large tolerance. So just to quickly pop this up, what we're looking at here is that there are relatively small differences in translation performance across similar window sizes. And we see slight instability with very small strides. So when we have basically majority overlap between image tokens, but the best ranges last for quite some time. So that's a good sign that we don't have to worry as much as you might wonder about particular hyperparameter settings. To go through quickly here, the relative training and inference speed is actually pretty similar to characters in BPE. It's right in between, in fact. So if we take BPE as our baseline, characters are about 2.5 times slower to train. And our best visual text setting is right about here. So a little bit faster than characters between BPE and characters. And it seems like rendering really doesn't add that much overhead. So we really didn't see any observable difference with BPE models at inference time when we're rendering sentences on the fly compared to tokenizing into subword sequences. So that's encouraging. All right, and finally, we don't really change the number of model parameters because we're basically exchanging the source embedding matrix for perhaps one convolutional layer. So the number of model parameters is actually pretty similar. So this is just a couple of technical details in case anyone was wondering, and we will carry on to robustness in a second, but I'm just gonna pause in case anyone has a question. Excellent, all right. So model robustness. This is really one of the main motivations for doing this work is robustness to rare phenomena, new characters, and ideally to remove some of the worry that rare or unseen things are going to cause the models to have very different representations than what they've seen in training and therefore do poorly. So ideally, we want to be able to interact with our models in the same way. So here I have a little video that will give you a preview of what's to come in the next couple slides. So we want to be able to interact with the models in the same way that we do a text-based model. And here we can.
We can interact with the visual text models directly, just like text input. For example, testing robustness with some character permutations. And what about visually similar characters? Great. So let's try the same sentences with a text-based model. A good start with normal input. An interesting turn with character permutations. And visually similar characters. Not so good.
So I did kind of cherry pick that second example, of course, where it said it was going to be a noisy model, but that is actually what the output I got using our TED trained German model. So as you'll see, there are many different ways that different types of noise can impact both text-based and to some degree visual text-based models. So we tested 5 types of noise as listed here, and I'll go through each of these in depth in the next couple slides. So first, diacritics and Unicode. So in the case of Arabic, it is sometimes the case that we have vowelized text rather than non-vowelized text. So for example, we have a number of diacritics inserted through the Unicode sequence. And it can be the case that we'll end up with Unicode noise, which here I'm using to refer to visually similar characters that are not actually from the language's code point range. So here, everything highlighted in red on the Russian side is actually a Latin character, which has been substituted for one that is visually similar in Russian. And so while these sequences look very similar to the original, they cause very different, very large changes to the underlying Unicode sequence. So for visual representations, which we've abbreviated here, visrep, you can see the extracted image windows and that we have relatively similar semantically translations to the original reference. Whereas the BPE models are backing off to predominantly characters, which really don't match what they've been using in training. And so we have very different output than we might expect. Looking at this quantitatively, so we have large changes to the Unicode sequences, but visually anywhere from only 0 to 5% of the pixels. So in this case, it's unsurprising that our method does so well because we are extracting visual features. So if things haven't changed much visually, we should be good to go. And in fact, that's what we see. So with increasing proportions of noise, so this is the probability that we're going to insert diacritics or Unicode noise per token. We see very little drop off for both Arabic and Russian, whereas the best subword models drop off pretty quickly. And it's honestly quite sneaky. This noise I had to check on the command line to produce this example, but it is occurring commonly in internet sources or things that have been OCR'd, for example, and the wrong code point range might have been used. So this is an example from a patent data set, which was constructed by using OCR to extract patent information in both Russian and English. What might be most surprising here, though, is that character-based models do not actually do very well for this task. So what I mentioned on the previous slide is that this noise causes a dramatic difference in the representations used at training time and inference time. But for a fully character-based model, we've only affected the sequence and the context of characters, but the representations are the same. But that is actually very important as well. And so it's not necessarily the case that character-based models are better than subwords for some of these types of noise. A fun one as well is leet speak. And this is one of the most common ones we were asked about when we were starting this project. So for leet speak, we're substituting visually similar characters in the same code point range. So here we are exchanging some letters for numbers. And so we see that this impacts the sequences in slightly different ways. So we have a relatively similar translation with the visrep model, but for BPE, the numbers are incorporated as if they're actual tokens. So for example, when with a 3 is translated to a third new hip. So for this situation, we see that the improvements are decreased, and I'm here showing blue just because these two languages have overlapping blue ranges, so it's kind of hard to read the plots if I don't show the delta. But here, the font choice, for example, might matter, going back to a question earlier. So for example, for different fonts, we have very different potential renderings for different characters, which may make, for example, the number and letter substitutions more or less similar. And there are also a number of confusable non-leet pairings, whereas this wasn't necessarily the case for Unicode noise. These are not canonical ways that people substitute in numbers for letters, but they're actually more visually similar than some of the mappings like E to 3. All right, character permutations. This might be one of the more challenging types of noise that we tried, in that it's not immediately obvious why visual text would be able to address this problem. So here, for swaps, we are making one swap between adjacent characters per token with some probability. And so again, we see that this is relatively easily handled by visrep models in a lot of cases, but not so much for BPE. So to highlight a couple of things before we go into these plots, I'm again showing improvement because with a lot of languages with different blue ranges, it's difficult to read otherwise, but you can see those plots if you are interested in an appendix. And then as well, we're probabilistically inducing noise. So this is in part based on the length of the tokens that we actually have in our data set. So for Korean, where for swap, I need 2 adjacent characters with shorter word sequences because we have done segmentation here. This is less common And definitely for the Cambridge model, where we're taking the first and last characters as constants and then permuting everything in between. So it requires a token of at least length 4. So depending on the sequence lengths after we've done word segmentation, basically, it may or may not be the case that we have as much noise induced. So a grain of salt there. So finally, what do we see? There are pretty significant improvements for all language pairs, even if there's a slight performance gap on clean text. So for example, we were slightly behind without any noise for Arabic, and yet we're able to do quite well here. So to highlight this best case, German English, when we have swaps on all tokens, the VisRep model remains pretty usable while the text model does not. The performance differences are not necessarily as significant for all languages though, but obviously there's something interesting and useful here. So what do we see about this compared to past types of noise? The previous types of noise I showed are typically substitutions rather than permutations. So it's a much more local effect. Permutations affect more character sequences within a given token, which really affect the way that BPE represents sequences. So for example, in this best case here, the German swap model, the BPE model used has to back off to many more subwords than without noise, and it's essentially using character sequences, which it really hasn't observed in training. Okay, cool. So this is all very nice, but all of the stuff that we just showed you is induced noise. And in a natural setting, there are going to be many additional types of noise and in combination with each other, whereas all these were individual types of noise in isolation. So to look at how we do on naturally noisy data, we used 2 test sets from Reddit and patent data. And we see that we're doing reasonably well, but obviously the results are not as dramatic as we just saw. The most important thing to note here is that these are different domains than we trained on. We're evaluating our TED models here in a 0-shot setting. So if you've only trained on TED Talks, you are naturally going to have some issues with Reddit and patent data where the language is very different. So unfortunately, domain is a confounding variable. In this particular scenario, the character level models are in some cases more robust than subwords, but in others they are not. And so visual text always does better than subwords and typically is on par with the character level models, if not slightly above or slightly below in some cases. So this is a little unsatisfying in that we'd hope to see similar performance, but the thing to do, I think, here is really to fine tune on these test sets so that we remove domain as an issue and then see for both models and see what happens. All right, so that was a big robustness section. Do we have any questions?
Yeah, there was a lot of great stuff with the robustness. Anyone have a question they'd like to ask Liz? Maybe we're just ready for the rest.
Sounds great. All right. Okay, so the next section is going to be improving text models. So the text models I've shown you are not necessarily naturally robust, but there are many ways that we can easily improve them. This can be done, for example, using pre-processing techniques like normalization, for example, Unicode normalization, which is a way that we can normalize visually similar characters to each other when they're in natural variation within a given keyboard setting. Or, for example, spell checkers. And then as well, model regularization. So this is something I will discuss in a couple slides. So what about normalization as pre-processing? It does help text models, but selectively. So it's really important to note that these types of approaches are language specific and best suited to observed noise or the types of noise that they were constructed for. And they rely on context to disambiguate. So with increasing amounts of noise, a spell checker will do worse and often require multiple passes to correct things after some words have already been resolved. So this is a gigantic table, but we're going to walk through it very specifically. So what we're looking at here is two settings. We have induced noise, and we're going to compare both our best BPE models and visual text models with and without adding spell check as a pre-processing task to remove a lot of the noise. So what do we see? Spell check generally helps BPE models, but it can actually also help BizRep models, as makes sense. So for example, adding in the swap case, a spell checker will resolve a lot of the degradation that we see due to noise for a BPE model, but it actually also improves the visual text-based model, which is good to know. Spell check doesn't help all languages equally. So for example, though we have a large improvement in French given swap noise, we actually see exactly the same result with German, suggesting that what corrections are being made might not actually be correct given the global context of the sentence. And all types of noise are not necessarily helped equally. So for example, spell checkers are really dependent on the types of noise that they've been constructed for, or in the case of, for example, a denoising autoencoder trained on. So if leet speak is something that they were never seen before, they will similarly not be able to help and may in fact hurt. And finally, just to really rub it in, I guess, spell check can also create errors. So as mentioned before, for the German swap, what we see is that there's no improvement for the BPE model, but we also see a large degradation for the BizRep model in that we're making our sentences essentially more noisy when we introduce errors. So this isn't a perfect fix. We can't necessarily just rely on normalization to remove some of the robustness issues that we have for any type of model. And as well, it's really important to remember that this is all only able to be constructed when we have data to create a spell checker or denoising autoencoder for a given language. Okay, so next up on our improvement pipeline is subword regularization or BPE dropout. So these are techniques that can often improve performance and robustness for BPE-based models. Are the improvements similar to what we see with visual text representations? Let's first really quickly remember what BPE is doing to create subwords. So we're going to take pairs of consecutive units, which occur with high frequency, and merge them into a single unit as we go through until we have a fixed number of merges created. So what BPE dropout is doing is saying, I will skip for this moment a certain number of merges. So this may be merges that weren't going to occur in that first step, for example, and so there will be no change. Or it could be the case that, for example, a merge that is skipped is the one that BPE naturally would have taken next. So the sequences of merges that are made are different and can result in different subword vocabularies than we might have otherwise. All right, so as just mentioned, BPE dropout is going to drop some candidate merges with some probability. And so when we're training our models, we can use different segmentations each epoch to increase robustness and the likelihood that we've seen representations like what we might see at inference time at some point during training. One potentially small problem is that a small number of the resulting subwords won't be in the downstream model's vocabulary. So if we've created a model vocabulary using a certain number of BPE merges, then it's possible that when we use a different BPE dropout segmentation for another epoch, some may not be in our model. The original paper and we as well saw that this happened in about 1% of cases and it didn't affect results. Subword regularization is a very similar and in fact the original way of using multiple different granularities like this through training. And so as a language model based approach, you can simply draw a larger stack of potential subword candidates from the model and use different candidate segmentations each epoch. So let's return to our question. Are the improvements similar to with visual text representations? In short, no. So both techniques provide very strong improvements over BPE or character models alone. And I actually really recommend now that going forward, people do adopt this as their standard. So we saw slightly larger improvements with BPE dropout than subword regularization, and I'll show more in the next slide. What we see, though, is that Visit models remain slightly more robust, even though with these improvements, their base performance is a fair bit lower now than the improved text models. So let's actually look at the results in graphical form to see this a little bit more clearly. So this is our initial comparison. So for Unicode and diacritics, we have Arabic and Russian, and then our text-based models here. And for swaps, we're looking at blue improvement for readability. And so this is the delta between our visual text models and standard BPE models. When we use subword regularization, we introduce a new line here. And you can see that there's a pretty significant improvement over the text-based model. On average, it's somewhere between 2 and 5 blue, depending on the language. And that's pretty cool, but there's still a large gap for both to Russian and Arabic. For swaps, we see that the improvements we get are reduced, but similarly by about the same range we saw over here, which is interesting again, because these are much more visually similar types of noise in my mind than, for example, character permutations. With BPE dropout, we introduce yet another line, and we can see here that the improvements are quite large. And in particular for Arabic, it's very similar both with and without BPE dropout to visual text representations. Why is this? By incorporating characters throughout training mixed with subwords, we're actually pretty well matched between training and inference because we've seen a lot of the context that we see with noise inserted in some way during training. So this insertion type noise is actually really well handled. This isn't necessarily the case for other types of noise though. And again, for swaps, we see a much more significant reduction in our improvements with BPE dropout, but we do still have improvements over the stronger baseline, particularly for some language pairs. So this is kind of encouraging, but it is a really important reminder that there are many ways to improve both of these models and from both. For example, maybe we should use multiple window sizes in training for the visual text models. All right, that was a deep dive on 2 ways to improve text models. Does anyone have any questions before I go on to future work?
I had a question, comment.
Sure.
Or maybe this will come up later, but have you thought about using the visual representations as a way, as just a pre-processing step, kind of like an OCR step on your text before you put it in the MT system?
That's a really good question. This has actually come up recently. So I have not. I think it would deal with a lot of the types of noise that we see here to just use this as a normalization step, but not necessarily all. So for example, like using an OCR model before MT to do cleanup, if you have perfect recognition, you're going to see, for example, elite speak sequence, and you're going to recognize the 4 as a 4 instead of, for example, a letter. So it depends on the way that you train it. I think that there are ways that that could definitely be perhaps a better or lighter way to do this. But yeah, I haven't experimented with it yet. So yeah, it's a really good idea.
Or maybe it only will help for the Unicode differences or something like that.
Yeah, that definitely. So for the Russian, for example, it might do away with this problem entirely. Yeah.
Great. Cool. Yeah. Any other questions?
All right.
Okay, let's continue.
Cool. so here we're just gonna have a couple open questions and future work before I conclude. So some clear next steps are, for example, pre-training or data augmentation. So all of the robustness results for both text and visual text models are zero shot. We've not actually trained or adapted to noise in any way, which similarly to not using, for example, spell checkers or, for example, subword regularization, we are kind of handicapping both of our models. So probably we can improve by doing this. Next is segmentation. So we use fixed size sliding windows. They work clearly, but they might not be optimal. And so actually having done some additional experiments there, I can say for sure that this is one of the reasons that we're a little bit behind on clean text because the windows that we're using are not optimal. In some languages, for example, if I do word level segmentation for Japanese or Chinese, and then render words rather than the entire sequence, such that our segments are basically word level units rather than a fixed width window, the gap closes. But then of course we remove some of our robustness improvements. So trying to figure out how to improve that would be great. And then finally, target side visual representations. Everything we did here was on the source side only. There is some preliminary work on this from Elman Mansanov et al. In 2020, but this is a really challenging task to translate directly to images and introduces potential evaluation complications because then you need to turn the image into text to evaluate for the most part. Luckily, robustness is typically a source side problem, but this can still be a wonderful extension to see. So some other natural future directions that I'd like to see, in addition to, for example, normalization, are transfer learning. So here we have an exacerbated challenge from the one that we see here, where predetermined vocabularies typically are not going to include all scripts. So often in multilingual models or any type of pre-trained model, the language, the vocabulary used is going to be biased toward what is seen in the pre-training task as opposed to how it's going to be used later. And we need to find some way to extend the vocabulary. But a visual text representation model can be used to transfer across scripts as is, because there's no tie to the particular vocabulary in one language. So I think that would be very cool to see and hopefully help with things like transferring between Slavic languages with and without Cyrillic. So that would be nice. And then finally, other NLP tasks like language ID have much more obvious and creative uses of Unicode. So for example, there's a wonderful table in this paper from last year, Language ID in the Wild, showcasing a lot of very creative ways that people can use different Unicode ranges. So for example, this Cherokee is not Cherokee, but rather using some of the characters from this range to creatively write in English. So for example, this might be a place where visual text representations could help. Other places this might help are languages that are either not included in Unicode or not really fully supported. So for example, a lot of the languages that are now attempting to be supported by the National Research Council in Canada don't actually have full Unicode support or Unicode normalization tables. So having multiple different sequences which can render the same way is a really pressing challenge to deal with. All right, so we've gone through some potential issues with Unicode-driven text representations and explored an alternate approach using visual text. These models are truly open vocabulary in the sense that we haven't committed to a fixed predetermined model vocabulary. And we see that this helps them be more robust than many types of text-based models and types of induced noise. There are a number of next steps, and I'd love to see this expanded for more languages and settings, though there probably are also limitations yet to be discovered. So I look forward to seeing what comes out in the future. And yeah, so that's it. We do have code and a paper which might be useful if you're curious about these in the future. And if you're watching or interested about this later, feel free to contact me after the talk as well. So yeah, thanks very much, everybody.
Yeah, let's thank our speaker today. So yeah, thank you, Liz. Is this an expanded version of the talk or what you shared at EMNOP?
Yeah, this is essentially a much deeper dive. So we have several appendices worth of material, which I was not able to share at EMNLP. So many of which, though not quite all, were discussed here today. So yeah, hopefully that makes the idea a little bit more accessible and helps anyone who's potentially interested in something similar to this. Yeah. So I will stop the share. If anyone has, oh, yep. So I see Lavon has a hand up.
First of all, I want to say thank you so much for this talk. It's super interesting. I think especially that last point about being able to transfer the languages without a shared script. That's is something that I spend a lot of time thinking about because I like to work with languages that don't use the Latin alphabet or any particularly commonly used ones. One thing I was wondering about is if you experimented at all with anything like romanization, because I know that some ad hoc romanization, well, first of all, it's ad hoc, so it's not super regular. So, you know, there's a lot of need for denoising and whatnot, but also some of it is based on visual similarity. And so it seems like a VisRep model might be, what's the word I'm looking for? It might be suited for the task. I'm sorry, the end of the quarter is really frying my brain.
No worries. I'm happy that you're all here, but if you're, you know, not at your most cohesive and asking questions, that's fine for me as well. But yeah, no, that's a really great point. And in fact, actually, I have not done this, but Maria Ruskina has work on using some visual features for romanization. So for example, for some languages, there are actually tables of visually similar Unicode characters. And so you can include those as potential candidates or information when you're trying to do romanization. So in that sense, I know that this is definitely potentially useful for romanization. I haven't compared to romanization for any of these tasks. I think if I were going to, for example, try this in a multilingual setting next, I definitely would want to. But yeah, not yet.
Thank you so much.
Yeah. Oh, and then, yeah, go for it.
Yeah, it was really awesome talk. Thank you.
Thanks.
I have two questions. One is, I mean, I'm not really familiar with OCR work, but how does this relate to OCR? Can this benefit from OCR? Can OCR benefit from this? And yeah, just how do you see the two relate?
Yeah, that's a really good question. And I guess what I maybe should have said earlier, when I was comparing to, for example, a much deeper convolutional stack for extracting features up front, I was actually using a setting from an OCR model that we have in-house, which does pretty well for that task. But it's a much heavier weight, basically, solution. So on the one hand, it adds a lot of parameters and training time, and it actually does slightly worse. So it seems to be the case that for OCR, you might be paying attention to much finer grained details or different aspects of the image than you actually need to if you're, for example, trying to figure out the minimum amount of information to be able to translate it. So maybe I just need to distinguish it from a different type of token, but I don't actually need to know exactly what's going on in the image. So for example, I tried adding an OCR loss right after that feature extraction, and almost always I did a little bit worse. So trying to actually be faithful to the characters that are in the sequence does seem to detract a little bit, at least for translation. So some ways though that there are really important things from OCR that might be useful for this task are, for example, the ways that you do data augmentation in OCR. So this might be including multiple fonts and training. So you've seen things in different settings and ways than you might with a single font, or adding visual noise. So if you have a little bit of, for example, noise in the sense of like light amounts of gray or pixelization or things like this, that can definitely help for OCR recognition. And it might help for noise in our case. But yeah, so they're definitely highly related, but not everything necessarily transfers, at least to machine translation from OCR. But
yeah, that makes a lot of sense. Thank you. And, I can circle back if someone else wants to go first, but I had another question. Or I can just go.
And you can go ahead and ask your second question.
Yeah, go for it.
Yeah, this is, I guess, more of me trying to understand part of the presentation. I'm not like fully sure why the character level models had such a big disadvantage compared to your method. So do you think maybe like if you further segmented the characters into subparts, just like manually, say like you encoded each character in like 4, like the top left, top right, whatever. Maybe is that going to come closer to your method because underlying that's something similar that's happening?
Yeah. So it really depended on the setting for character-based models, essentially. So what we saw, for example, is that if you have insertions in a character sequence, you've kind of broken up the context for all of the characters that you would have seen beforehand. So the model isn't necessarily able to get a chunk that it recognizes from what it's seen before and handle it perhaps appropriately. Whereas, for example, if you have permutations where I'm only doing one permutation per token, you have a number of consecutive character sequences around that permutation that are the same as what they would have been before. So for different types of noise, character-based models seem to handle them a little bit more easily or not, based on the way that the noise affects the similarity of the distribution at inference time and for training. So yeah, so that was one of the hard parts for us, was finding an appropriate comparison when, for example, character models did very poorly on the Unicode noise, but better on diacritization. And so the BPE dropout and subword regularization are kind of mixing characters and subwords throughout training, and seem to help a lot for those situations where having similar character sequences or contexts at training and inference time might help most, but having that mixture really seems important. But I imagine that all these would do better if trained on noise. So for example, if I'd actually trained a character-based model on both vowelized and unvowelized Arabic, I imagine it would have done far better than it did. So that's my intuitions on that part. And if there was anything I missed in the question, please feel free to ask again.
No, that was awesome. Yeah, thank you again for the great talk.
Awesome. Yeah, thanks everyone for coming and for being engaged at the end of the term as well. So yeah, this is great.
There's a comment for you to read in the comment section. Yeah. And yeah, any last thoughts, or I don't know, wanting to pick Liz's brain or anything? Yeah, I think I don't have any other questions either. I a lot of creativity and I think good things to think about from this talk. So again, I really thank you. I'll stop the recording here. Stop.